So far, we've only looked at simple harmonic motion. Simple because we are just assuming that the vibration continues forever. Simple harmonic motion means cos omega t, uh, constant amplitude. That would look something like this. Here's a wine glass vibrating in simple harmonic motion. It would vibrate forever. We know that's simply not true. The vibration dies off. So we want to include the effect of this dying off of the vibrations. Now, why do vibrations die off? It's because, and we see it here, here's an actual vibrating system, some weight on a spring. The vibration amplitude decays as time goes on. You see the height is not maintained, but the vibration gets smaller and smaller. When you ring a bell, the bell doesn't ring forever in simple harmonic motion. It's actually what we call damped harmonic motion, where the effects of the air and internal stress within the bell kill off the vibration as time goes on. So how do we model this? Here we have, not shown, but above the animation is a spring, and there's a little disc which extends into the liquid. As the liquid moves, it drags against the fluid. That produces the damping effect. It's just like waving your hand in the air, and when your hand moves, you feel the air pushing back on your hand in the opposite direction. That would be air resistance. In general, it's some kind of fluid resistance which produces the damping effect. So we'd like to model it and include it in Newton's law. So now Newton's law is going to tell me that the mass times acceleration needs to include not only the restoring force, but the effect of the damping as well. So let me actually sketch it first. So here's our spring that produces the restoring force. We've got a mass attached to that spring. And then the damping is produced by some kind of a damper which moves in a fluid. So here's the damper, like the disc, that moves inside the liquid, and it produces a damping effect upon its motion. So Newton's law has to include, of course, the restoring force, but now also the damping force. And think of how air resistance works. The only time you feel air resistance is when the object has velocity in the air. You only feel the air when you move your hand through the air. So it's a velocity-dependent force. And we'd include it like this. Notice, first of all, it's minus the velocity. So when the mass is moving to the right, the damping effect is to the left. And when the mass happens to be moving to the left, the fluid produces a damping force to the right. It's minus the velocity. And it's simply proportional to it. The proportionality is a force constant known as the damping coefficient. Its units are newtons per unit of velocity, newtons divided by meters per second. So we have a new term in Newton's law that's of course going to change the type of motion that's produced. And we already know that one major effect it has is it makes the vibration die off. It now makes the amplitude reduce with time. Another effect that it has, so there are two main effects. Another effect that it has is it changes the frequency that the system vibrates at. You see, without damping, we know it will just undergo simple harmonic motion with a frequency that we'll now call omega naught, indicating zero damping, and it's just root k over m. However, with damping, the frequency is altered, and the frequency of the motion, which I'll call now omega 1, the frequency with damping is less. and you calculate it by taking omega naught and squaring it, and you subtract off a piece that depends on the damping, it turns out to be B over 2m. And you got to square that, and you combine the two terms under the square root. So notice that omega 1 with the damping is smaller than omega naught. You're subtracting off this damping piece here. Now, the second effect, without damping, the amplitude is just constant. With damping, as we saw, the motion dies off and the amplitude decays with time. In fact, now the amplitude is now a function of time, and it turns out that it decays in an exponential fashion. So now the amplitude is some constant a multiplied by a decaying exponential, e to the minus t. It is a constant in there, e to the minus b over 2m times t. So you see, now as time goes on, the amplitude gets smaller and smaller. So those are two main effects, and we can put it together, put both ingredients together to describe the motion when there's damping present here. So now x of t, well, let me put down without damping. Without damping, we know that x of t is given by a cos omega t with a phase angle in there that describes the initial conditions. With damping present, now the solution is x is this decaying amplitude. And now it's still multiplied by cos omega t, but it's a different frequency, omega 1t, with a phase. So that's the essential, those are the essential ingredients of damped motion. Now, it's worth noting that something unusual happens if the damping coefficient is very big. If the damping coefficient is small, then it still vibrates, just the amplitude dies off. Let me show that again. Here, the water bottles, the amplitude dies off with time. It gets smaller and smaller. Here's another way where we could control the damping effect. This is a magnetic damper. What you have on the end of this ruler is a magnet, and there's a sheet of aluminum behind it. When a magnet moves near metal, there's an interaction which acts like a damper. And so we see that here, the pendulum motion dies off fairly quickly because of the interaction between the magnet and the metal. So that's what happens when B is small. And when B is small enough, we call that underdamped. And so that's not going to, it still vibrates. However, if the damping effect is very large, note what happens. It completely breaks the motion, B-R-A-K-E, breaks. It acts like a magnetic brake, and it doesn't even vibrate at all. It just settles down to the equilibrium. So how big does the damping coefficient have to be until there's no vibration at all? We can easily see because look, with damping present, the frequency is smaller. If B is very large, the frequency can become zero, and zero frequency means it's not a vibrating function at all. There is no vibration. So when does that happen? Well, I can tell that if B over 2m is equal to omega naught, then you'll have absolutely no damping at all. I mean, no vibration at all. We call that the critical value of B. Okay, so there are in fact three cases. There's what's called underdamped, which means there's not too much damping at all. Underdamped is when B over 2m is smaller than omega naught. It does vibrate, it decays, but there is vibration present. There's critically damped, where if B over 2m is actually big enough that it equals omega naught, then there's omega 1's equal to 0 and there's no vibration at all. And then if it's bigger than that, you call it overdamped. B is so big that it's B over 2m is greater than omega naught. And then in that case, there's no vibration there either. You could tell that because actually omega 1, the square root under the square root becomes negative, indicating imaginary frequency, which actually indicates just even stronger damping effect. That's what you want. Critically damped or overdamped is what you want with the shocks on your car. You don't actually want the shocks to make the car vibrate when you hit a bump. You want there to be enough damping so the vibration is rapidly dies off. Next, we'll look at an example of a vibrating system which is damped. Here's an example of a damped oscillator. It's something like a diving board, where we model a diving board as a rod attached to a spring that makes it vibrate. What we're told is, with no damping, the period is T naught. With damping present, the period is T. We know that's to be expected. With damping around, the frequency is a bit less. In other words, the period's going to be greater when there's damping around. From these two values, we want to determine what the damping coefficient is. The idea being I compare the two frequencies and they basically differ by the value of the damping coefficient. Okay, so let's first look at it without damping. I'll write down Newton's law and we'll look at the solution. We'll compare that to Newton's law with damping around. Now, this is a system that undergoes angular motion, so it's going to be torque. Notice that the spring produces a torque on the rod depending on the stretch that it has. I'll call it Y. Y is the extension of the spring. So what I'll do is I'll write down Newton's law. This is going to be without damping first. So I'll have I alpha, that's the inertia of the rod times its angular acceleration, is equal to the torque from the spring. The torque from the spring is going to be minus L. Oh, and by the way, I'm assuming small angles, as usual. Assume theta is very small. This is a small vibration. So the torque will be L multiplied by the force of the spring. That'll be minus L times ky. Again, theta is very small, so even when the rod is up here, the rod is basically perpendicular to the spring. That's the assumption I'm making from a small angle. It's similar to the wheel problem we did earlier. Okay, so the torque is minus L times the force of the spring, and we get, now I use the small angle to express y. Y is going to be L sine theta, which is just nearly L theta. Again, basically the same as what we saw in the wheel example before. And that gives me the torque of the spring in this approximation comes out to be minus KL squared theta. So again, it is a simple harmonic oscillator. It absolutely is because I see that the acceleration is proportional to the displacement. In fact, I can read off I can read off the value of omega. I'll call it omega naught because it's without damping. Omega naught squared is equal to KL squared divided by the inertia. Now let's see what we have with the damping around. The spring is unaffected, so I have I alpha is equal to the same torque from the spring, minus KL squared theta. But now there's a new ingredient. Now there is a damping effect from, I guess, the air that it's moving in. And I'm assuming the damping effect is proportional to the angular velocity that it has. So it's a damping coefficient times angular velocity d theta dt. I don't want to call the angular velocity omega because that's going to clash with our notation for the frequency of the vibration. So I'm just spelling out exactly what it is, d theta dt. Okay, so we've seen previously how to handle this. I know this is a damped oscillator because I've got the restoring term and I've got the damping term. And so I now know what omega 1 is going to be. Let's write omega 1 squared to get rid of the square root. It's omega naught squared minus, now when it was a linear system like a mass on a spring, it was B divided by 2m. That's because Newton's law involved B and m on the left side. But in this case, it's going to be B over 2I, that quantity squared. It's the same as the spring problem, it's just things have different names. Instead of m, it's inertia. Instead of A, it's alpha, and so on. So I see that with the damping, omega 1 is certainly smaller than omega naught. And in fact, I can use this expression to solve for B. This is an equation to solve for B. You see, it tells me that B, actually tells me that B squared is equal to 4I squared times the quantity omega naught squared minus omega 1 squared. Now I'm actually given the periods. Remember that omega naught would be 2 pi over t naught, and omega 1 would be 2 pi over t. And so I can plug in those values for omega, for the omegas, and I actually know then what the value of b is. Typically in practice, this is the only way you're going to figure out what the value of the damping coefficient is. Compare the frequency without the damping, then you put it in the fluid and compare what the frequency is in that case. And let's just figure out the damping coefficient.